Alright, our next one is back with the magnetic fields. The statement reads, the magnetic field of an infinite straight wire carrying a steady current I can be obtained from the displacement current term in Ampère Maxwell's law, as follows. Picture the current as consisting of a uniform line charge lambda moving with the z-axis along the z-axis at a speed of v so that I is equal to lambda v, with a tiny gap of length epsilon, which reaches the origin at time t equals 0. In the next instant, up to t equal epsilon divided by v, okay, so distance divided by the velocity gives us time, there is no real current passing through a circular Ampérian loop in the xy plane, but there is a displacement current due to the missing charge in the gap. Alright. A. Use Coulomb's law to determine the z component of the electric field for points in the xy plane, a distance s from the origin, due to a segment of wire with uniform density negative lambda extending from z1 equal vt minus epsilon to z2 v equals zt. Again, we kind of saw this a couple questions ago with the dynamic variables, quote unquote. And then B, determine the flux of the electric field through the circle of radius A in the xy plane. C, find the displacement current through the circle, show that ID, the displacement current, is equal to I in a limit as the gap width E or epsilon goes to 0. Alright, let's draw out what we're talking about here because it's going to be a mess otherwise. So here we have some line charge lambda moving on the z-axis, right? And so we have our locations of z with respect to the velocity it's moving and time. So we see v of t to the right and v of t minus epsilon to the left, since epsilon has to catch up to it. And clearly the point that we're taken from at negative z, the field line, the separation vector r, script r, will pass through the y-axis, and then we see that the differential field there, the E, is formed at some angle theta to the y-axis. Alright, so let's go ahead and chug this along. Clearly, if we're concerned with the field only in the z direction, dEz is equal to 1 over 4 pi epsilon naught negative lambda dz over script r squared sine theta. Okay, remember that cosine theta would put it on the y direction. Now from sine theta from the diagram, we see that sine theta is equal to negative z over script r. Put it all together, we see that script r here is equal to negative z squared plus s squared. Therefore, the square root is equal to z squared plus s squared. We'll put that to the 1/2 power since we're going to have 3 of them in the denominator. So integrating this to find the electric field gives us 1 over 4 pi epsilon naught negative lambda over script r squared negative z over script r dz. Alright, so now what we can do is take the lambda and 4 pi epsilon naught out, and we're left with z over the script r cubed, so we can now plug that in. Now z again was running from v of t to v of t minus, or v of t minus epsilon to v of t, again shown in the diagram, and we see that we have z over z squared plus s squared to the 3s power. Let that calculus work through. You get negative 1 over z squared plus s squared to the 1/2 power, and then evaluate it all. So Ez here, as you see, is equal to lambda over 4 pi epsilon naught times, in the brackets, 1 over square root vt minus epsilon naught squared plus s squared, and then the same thing, but with vt. Alright, so the flux through the circle then is flux E is equal to 0 to 2 pi, 0 to a, since that's our bounds, 4 pi over epsilon naught, or times Ez in this case, and that is s ds d phi for our integral. Let it work its way out. That s will, if you do a u sub on it, will make this much easier. So now we're left with this, instead of being 1 over, we're just left with the square root, because negative 1/2 to 1/2, that whole thing, in the integral. Nonetheless, let it carry through, and we see that the flux is equal to lambda over 2 epsilon naught, since the 2 pi's cancel. And then we're left with this square root term minus square root term, minus, since 0 goes in there and the square root cancels with the square, minus vt, and then a minus, hence the plus vt term at the end. Since we want the current, we see that I is equal to epsilon naught d phi of the electric flux dt. We can go ahead and solve this through. Be very careful with that derivative. Now you see we're stuck back with square roots and denominators, but otherwise pretty easy to deal with. Yeah, and then you get a minus. Yeah, yep. And then you see the other terms just kind of vanish and do away. You see we get a lot of v's by themselves. All right, so with that, they wanted us to take the limit as epsilon goes to 0, which means that v of t is much less than 0, or not much less, but is less than epsilon, and also goes to 0. So with this, we say that the displacement current, with all of that together, goes to 0. The fractions go to 0, so we're left with lambda over 2 times 2v. The 2's cancel, leaving us with lambda v, which is equal to I, and we're good. With an infinitesimal gap, we attribute the magnetic field to the displacement current instead of the real current, but it's the same answer. That's a mess, but that was fun.